Hi, everybody. Welcome back to another episode of Dr. Blitz Peer Reviews. Today, we're going to be talking about this paper, Controlled Closed Time-like Geodesics in a Rotating Alcubierre Spacetime. By the way, I did get new glasses, for those of you who are interested. So, just from the title alone, it looks like this paper is probably going to be about time travel. That's what closed time-like geodesics are, and they're going to be using Alcubierre drives to do so. So, it should be quite interesting, I think. Why don't we get started, and we'll start with the abstract, how about? So, we present two modifications to the rotating Alcubierre metric. Now, they give a citation here. Let's go take a look at what that citation is. So this is a paper called Spinning Up a Time Machine. Maybe we should read this paper first. Let's find out. Is this paper long? How long is this paper? This paper is only... Actually... Let's read this paper first, because this paper might be more interesting, or at least it'll give us some background, and then we can read the other paper at a later date. So let's read this paper first. It's only 5 pages long, has some great diagrams, it looks like. Let's read this paper. So instead, we're going to be reading this paper by T.C. Ralph and Chris Chang, Spinning Up a Time Machine. So this one is going to be presumably using an Alcubierre warp drive to build closed time-like curves. Right, so let's start with the abstract. We present a global metric describing closed time-like curves embedded in Minkowski spacetime. So, just as a reference here, a metric is a way of measuring the curvature of spacetime, kind of the shape of spacetime, and a closed time-like curve is kind of as it sounds. It's a curve that closes in on itself in spacetime, so think of like a loop, but it's time-like, so every direction that you go along the curve, you're still moving forward in time. However, because it's closed, it has to go back in time to meet back with itself. So in some sense, you're traveling forward in time while going backwards in time. This is a time machine. And they're embedding it in Minkowski spacetime. So they're just imagining, can we kind of put this on top of regular flat spacetime? Now they say, physically, the metric represents an Alcubierre warp drive on a rotating platform. So they're going to take a normal warp drive that you may have heard of, the Alcubierre drive, and they're going to rotate it. Okay, fine. The physical realizability of such a metric is uncertain due to the exotic matter required to produce it. So this is true. The Alcubierre drive is famously unrealizable. You can't make one because it requires matter with negative mass. But let's set that trouble aside and just see what we can do. Nevertheless, we suggest that this metric will have applications in more rigorously studying the behavior of quantum fields interacting with closed time-like curves. Interesting. Okay. So that's where we're going to go. So, all right. I don't actually know. Well, this paper is cited at least once, so it's probably fine. So, the wormhole solution of Morris, Thorne, and Yurtsever generated much interest in closed time-like curves because it suggested that they may exist in our own universe, as opposed to earlier solutions which had been restricted to different cosmologies. So my guess is that they're saying something along the lines of, well, so there are closed time-like curve cosmologies, universes that have closed time-like curves. The famous one is the Gödel or is the Tipler cylinder. However, that's not our universe, but it seems like there's this other solution, which is the Morris, Thorne, and Yurtsever solution, which also can have closed time-like curves in our universe. So it's at least interesting. In turn, such schemes have been criticized on various grounds. Oh, okay. So far, the argument appears undecided. Fine. In the end, it seems all such discussions require assumptions to be made about the nature of the so far undiscovered complete theory of quantum gravity. Whether CTCs are closed time-like curves, exist or not appears to depend on these assumptions. This is a fairly conservative take, namely that if you want to understand time travel or closed time-like curves, you need to understand a full theory of quantum gravity, which we don't have yet. We only have classical gravity. This is general relativity from Einstein. Now, they go on to say, assuming CTCs do exist, actually, you know what? Let me do this. It's probably better. Assuming CTCs do exist, a particular interest for some researchers are situated where quantum particles coming from the past in flat space interact with CTCs before proceeding on to the future in flat space. So here we have a solution where you have a particle coming in, it goes around a closed time-like curve, and then it goes out again. That's kind of strange. I have reason to think that that's probably not possible, but let's proceed. However, while the solution of reference 1 suggests that this sort of interaction is possible, it does not explicitly allow one to model such an interaction, as there is no explicit connection between the asymptotically flat spacetime and the two mouths of the wormhole. Okay, so here we're actually talking about CTCs via wormholes, not the traditional CTCs, which is a different... Well, so it's CTCs via the wormhole. So in principle, I guess they're saying that it's in principle possible for this to happen. I'd have to go look at reference 1, but I'm not going to do that. Let's just keep reading. Whilst one could, in principle, transform between reference frames in order to patch together the desired evolutions, this is challenging in practice. One could patch together the desired evolutions. Yeah, okay. Other solutions are similar, with various exotic spacetimes allowing for CTCs in principle, but not containing them explicitly, or not allowing an explicit connection between the CTC and the chronology-preserving objects in flat space, but rather requiring a patching together of different reference frames. So the idea is that nobody's really like working with like a full solution of gravity that has closed time-like curves. Rather, they're kind of just saying like, oh, we're just going to put a time-like curve solution, closed time-like curve solution in, and we're just going to like glue it to regular spacetime. But that's not really like a clean way of doing it, and it might not even be a correct way of doing it. So they say exceptions are certain ad hoc metrics. As a result, research into quantum objects interacting with CTCs has used very simple toy models, which simply model the CTCs with unusual boundary conditions. Okay, fine. So I think that they're actually going to try to build an explicit metric with a closed time-like curve. Let's see. We will investigate faster-than-light time machines here and be specifically interested in the warp drive metric introduced by Miguel Alcubierre. So this is the standard time machine. It's the contracting, or the standard faster-than-light machine. Contracting space in front of you, expanding space behind you. You can move through space faster than light. We can't actually make such a thing because it requires negative matter or negative mass matter, but it's at least like a well-studied example of a faster-than-light warp drive. The warp drive spacetime forms a bubble around a region with it says right here, with contracted spacetime in front and expanded behind. These contractions could push the pocket of spacetime at velocities that are not limited by the speed of light. Regular limits on the speed of objects exist due to their motion through space, and so the pocket of space itself does not experience those same limits. Spacetime is flat, scrolling over, is flat at the center of the bubble, hence an observer at this point would be in free fall. Their geodesic is time-like with no time dilation with respect to outside of the bubble. As for wormholes, exotic matter and energy is required in order to create the warp drive. Though some work has looked at reducing these requirements, it is not known if the required exotic matter energy requirements can be met. For the purposes of this analysis, we will simply assume that they can. So they're going to say, look, there are a lot of problems with warp drives, with time machines, with closed time-like curves. These are, in some sense, they are physics problems, but they're just going to say, assume that all of those problems are not there. What can we actually say about these things? That's the whole purpose here. And yes, by the way, this will be going on YouTube. If one is allowed to travel faster than light, then time loops are a natural result. Yeah, that's true. If you travel faster than light, you can go back in time. Consider the following two-journey scenario. In the first journey, with respect to some inertial reference frame, a traveler moves faster than light to a secondary position, some distance away. So you use your faster than light machine to jump to some other distance, some other distance in a very short time. From the viewpoint of an observer in a different inertial reference frame traveling at some high velocity relative to the first, the temporal order of the space-like separated events, so temporal order is just whether it's in the past or the future, and the space-like separated events are basically moments in space-time that are connected by a path that moves faster than the speed of light. So from the viewpoint of an observer in a different inertial reference frame traveling at some high velocity relative to the first, the temporal order of the space-like separated events describing the departure and arrival of the time traveler may be reversed. So the idea is that depending on how fast you're moving, things that might be simultaneous in one frame might not be simultaneous in another frame. And so in fact, if you move faster than light, things that might be past then future in one frame go future then past in another frame. For this observer, a return journey back from the traveler's arrival position to the origin at a finite but also superluminal velocity could allow the traveler to arrive back at their original position at the same time or earlier than they had left. So this is the business of how you might time travel, at least from one observer's perspectives. So, we'll see where they go. Everett of Hugh Everett fame, interestingly enough. Everett suggested a protocol based on the Alcubierre warp. I think that's Hugh Everett. I'm curious. Different Everett, actually. Different Everett, not Hugh Everett. Not the many worlds Everett. Everett suggested a protocol based on the Alcubierre warp drive and the logic of the previous paragraph that would enable backward time travel. So they're going to walk us through their explanation. Let's see what it says. Consider two warp drive bubbles, each defined in inertial reference frames related by a boost propagating in opposite directions. So, basically, you have two warp drive bubbles moving in opposite directions. Yeah, okay. That's what they're saying here. The traveler uses one bubble to travel superluminally between 2 points. Okay. They then accelerate to match velocities with the reference frame containing the second bubble, and use it to travel back to their original position superluminally. So they're basically, so you have two bubbles going in opposite directions. They take one to get somewhere, then they speed up in a normal way. They speed up in a normal way with a normal rocket, hop inside the second bubble, and then travel back, both at the speed of light. In principle, if the trajectories of the bubbles and the travelers are arranged just right, and the boost is sufficiently large, then the traveler can arrive back at their original position before they left. So this would require some space-time diagrams to work out, but at least in principle, it seems plausible. Then the traveler... So intriguing as this is, the arrangement is complicated and requires several changes of reference frame to follow the path of the traveler. It has been suggested that all faster-than-light time machines rely on multiple separate journeys in this way. So, yeah, I mean, it makes sense. This is a complicated example. But we'll see what they have to say. I assume that they're going to give us a better explanation. Yeah, here it is. Here, we propose a single journey time machine based on faster-than-light travel. We introduce a single global metric describing backwards in time trajectories for massive particles, allowing for the formation of closed time-like curves, and a local metric which describes how events are perceived by local observers. Well, that's handy. So they're going to give us a metric that tells us how things work. These trajectories are embedded in Minkowski spacetime, allowing particles to begin and end their journeys in flat spacetime. To our knowledge, metrics of this type have not been described before. So basically what they're going to be doing is they're going to be basically describing a certain spacetime, which is potentially realizable in our universe, that allows for using a warp drive, presumably a rotating warp drive, that allows for backwards time travel. So we'll see what they have to say. Okay, so first they have to describe the spacetime to us. So here's the global metric. The global metric just means the spacetime. The coordinates we will use to describe our system are rotating cylindrical coordinates. See figure 1a. Let's go see figure 1a. So figure 1a, so here are the coordinates. So z, I don't know if you can see this, z is coming in and out of the screen. And then we have a Greek letter phi, which goes around in a circle. And then you have a radius r, which is distance away from the center. And then you have a clock t. That ticks along, no problem. And the... do they say... and so the coordinates are actually rotating. So r is rotating with time. So it's a rotating... so it's a rotating coordinate system. Anyway. The metric for flat space in these coordinates is given by 16. So all they're doing is... for those who are just getting with us, this paper is called Spinning Up a Time Machine. It was written 4 years ago. But it seems interesting, and it was referenced in a paper I wanted to read. So it's called Spinning Up a Time Machine by T.C. Ralph and Chris Chang. Anyway. So all they're doing is they're going to describe regular flat spacetime, but in these strange coordinates, in these rotating coordinates. So in particular, we're going to have a mixing between the angular position and the time position. And that's exactly what we see. So in particular, you have some time. Your time is, maybe you can pin the description in the chat. Probably not. So what's happening is that there is some degree of time dilation, because if you're at a fixed position r with no changing phi coordinate and no changing z coordinate, that means that you're rotating with the coordinates, and so your time is going to be warped. This term here, this dt squared term, that tells you roughly how much time dilation there is. So the bigger your r is, the further out from the center, the faster you're moving, and so the more your time is dilated. Then there's this mixing term, which basically says that your angle and the angle and time coordinates are kind of mixing together because you're describing a rotating system, which checks out. Then you have your normal, this is just how you measure angles. This is this d phi squared. It's just the arc length of a circle drawn by, at a radius r, has length r times d phi, and then you square the whole thing. By the way, this ds squared is basically just a measure. It's like the equivalent of the c squared term in the Pythagorean theorem, a squared plus b squared equals c squared. So they're just describing how you can calculate distances and times in space-time. And then you have dr squared, which is just the normal length squared. That's your say your b squared. And then you have a dz squared because we're in 4 dimensions. So you need a distance away from the center, you need an angle, and then you need a height, say above the screen. So that's 3 spatial dimensions, then you have time. So they even describe it. Here, r is the radial coordinate. So this is the coordinate that points out from the center. Theta is the angle in the xy plane. The parameter omega is the angular velocity around the z-axis. So this is the spinning, right? An object rotating around the z-axis at this angular velocity will be at a constant phi in these coordinates. So if you're already spinning around the z-axis at that rate, at the angular velocity omega, then your phi coordinate will be fixed. Can time really be defined as another dimension? Absolutely, that's what we do in relativity. The time coordinate t can be thought of as that told by a clock at the origin, and therefore is not a function of the rotation. So t actually doesn't matter, or t actually doesn't change. It's your internal clock that'll change if you're moving with the rotating coordinate system. When omega equals 0, the metric reduces to the usual description of flat space and cylindrical coordinates. So we can just take a look. So set omega to 0. So throw away this term, and you're just left with dt squared and then cylindrical coordinates. So it's totally well defined. This isn't spherical coordinates. This is rotating cylindrical coordinates. But anyway. The tangential speed of light at a particular radius in terms of these coordinates will be of interest. Okay, that's a good point. The tangential light cone at a radius r is given by vc as 1 plus or minus omega r. And that checks out, because if you plug in 1 plus or minus omega r, you'll get this term, and you'll get that it's 0. Now, the anisotropy of light speed in the tangential directions in a rotating frame leads to the well-known Sagnac effect in optics. Yeah, so if you're in a rotating frame, the speed of light is different depending on which direction you're moving in. If you're moving with the rotation, then the speed of light is faster. If you're moving slower, if you're moving against the rotation, your speed of light is slower. Okay, great. Drink some water. By the way, y'all, like the live so we can get more people in here. Oh, TR, thank you for the subscription. Thank you for renewing your subscription. Right. We now set omega equals to 0, so they're going to imagine that it's not rotating, and consider an Alcubierre warp drive with a circular trajectory in the xy plane, which maintains it at a constant radius, r sub s. Let's go look at figure 1b. So here, what they're imagining is you have an Alcubierre bubble that's going in a circle. So the reference frame, we want this one. The reference frame is fixed. However, the Alcubierre bubble is moving in a circle. So it's moving potentially faster than light, and moving in a circle in the cylindrical coordinate system. So then the metric described by the Alcubierre bubble moving in a circle is given by this metric, which is very, very similar to the one that we saw before. It's like the rotating metric, except here we have this. We have 2 extra terms. Rather than having omega r, we have omega r and omega r squared. Here we have fv and fv squared. So here they're going to tell us what these are. Are they going to tell us what v is? Oh, they do tell us what v is. V is the rate at which the Alcubierre bubble is moving around. So that's just the speed. And then f, which is f of ds squared, is a smooth function of the squared distance between the space-time point of interest and a trajectory of constant r equals rs and z equals 0, and time-varying phase. So, wait a minute, what does that mean? Let's think about this. It's a smooth function of the squared distance between the space-time point of interest and a trajectory of constant r. Oh, okay, I see. So, yeah, okay, let's think about this for a minute. So they're actually going to give us a specific example of ds squared. So they're going to let ds squared be r squared, which is the distance from the center to the spacetime point of interest, plus r sub s squared, which is just this distance here, the distance to I guess the point where the Alcubierre drive is moving in a circle, and then subtracting off some term. I don't know why they're choosing this. So they're subtracting off a cross term, which involves the phase and the radius as well. Hopefully they'll explain where this comes from. And then they add some z squared as well. That's just because that's the distance from the vertical distance from the origin, which is fine. So this is a smooth function. It's just some smooth function. They're just defining it this way. And then they just require that f of d sub s squared is 1 when d sub s squared is 0. And it smoothly goes to 0 as d sub s squared goes to r, where r is some finite positive number. So basically f is just a function that is 1 when the... Yeah, it's 1 when d sub s squared is 0. So it's just a function. It's just some sort of smoothing function. And it goes to 0 when d sub s squared is some positive number. Ah, I see. Okay. So you have a time-varying phase. This is a basically tells you where around the circle you are. And that just is some function of time, right? It's just telling you some function of time. And so the point is that this f of d sub s squared basically tells you how far away some point of interest is from a point that's moving around the cylinder at a particular rate. And so that's what this is saying in particular. And so you have this difference here. This is roughly r minus r sub s and then all squared, except you have to account for the phase difference is changing. So this does check out. So basically, if you're following the time varying phase exactly, then d sub s squared is 0. So if, say, the time varying phase, you can't see if the time varying phase is moving at, say, a constant rate, and you just were asking what the d sub s squared was for a point that was in that constant rate, it would be 0. And it just goes away from 0 close. It goes to, sorry. The d sub s squared would be 0, and so f of d sub s squared would be 1. And then f of d sub s squared goes to 0 as you move away from that time-varying position. V sub s is just a speed. But they're going to explain that in a minute. Right, okay. So they also define v sub s of t as r sub s times the rate of change of the phase. So this is basically this is just the speed at which this trajectory at constant r is moving around the circle. So all they're setting up is a function that is moving around a circle at a particular rate. And the space-time is not doing anything if you're not part of that circle that's moving around. So that's all we're looking at. So the space-time is curved in an area that's moving around the space-time, and otherwise it's flat. Okay. For those of you who are just joining us, we are reading Spinning Up a Time Machine by T.C. Ralph and Chris Chang. It's published 4 years, or it was written 4 years ago. Right, let's continue. And importantly, when V goes to C, nothing bad happens because this is an Alcubierre drive. So, what do they say? Notice that if we consider incremental translations in the tangential direction, so imagine kind of ticking along in the circle, and hence since set rd phi to dx, we obtain the original Alcubierre metric. So all they're saying is that this is basically the regular Alcubierre metric, but it's just kind of curved around. So usually the Alcubierre metric just describes a warp bubble moving in a straight line. They've just curved that line around. That's all they've done. Tangential light cones with f equals 1 are given by... So here they're saying what... So tangential light cones are just the... roughly the speed of light in various directions along the direction of motion. And so at the location where your spacetime is curved, where you have this Alcubierre drive kind of wrapped in a circle, the speed of light in the direction of travel is faster. It's v sub s plus 1, and the speed of light against the direction of travel is v sub s minus 1. In particular, they say that we see a particle moving along with the bubble, following a circular trajectory with tangential velocity v sub s, will be following a locally time-like trajectory. So, in particular, v sub s, something moving at v sub s, will not be moving faster than the speed of light. And because they're lying between the light cones, even if v sub s is greater than 1. So even if relative to the stationary spacetime, v sub s is faster than light, relative to the spacetime within the bubble, you're moving slower than light. So it's perfectly allowed for an object to just exist in there. Okay, so this is the setup. It's a lot of warm up, but we'll get there. We now introduce the time machine metric. All right, that wasn't the time machine metric, but we're going to get there. We will presently show that this metric represents an Alcubierre warp drive with a circular trajectory as described above, but now on a platform rotating at angular velocity omega. Whew, okay, this is confusing. So, what they have... So they're going to have the Alcubierre drive moving in a circle while the Alcubierre drive is sitting... So it's going to like race around a platform while the whole thing itself is spinning. Ooh, lots of rotation here. A global description of this situation is given by the following metric in our rotational cylindrical coordinates. Huh. Oh, thank you for the sunglasses, Heidi. Much appreciated. So all they're doing is they're just going to slap in the rotating coordinates, or the rotating metric, and they're going to slap on top of that the Alcubierre drive. Sorry, they're going to slap in the cylindrical rotating coordinates, and then on top of that, they're going to slap in the Alcubierre drive. Yes, hence the title of the paper, Spinning Up a Time Machine. Right. So, what do they have to say about this? So a global description of this situation. So you have a warp bubble, a warp drive, going in a circle while sitting on top of a rotating platform. The metric looks like this. So we have two terms for the dt squared term. This is how the time is warped. We have two terms contributing here. One is from the warp drive, and one is from the rotating coordinate system. Fine. This next term, one of the terms comes from the warp drive, this f times v sub s times r. And then it has another term, which is minus omega r. So this is a interesting cross term. It wasn't there before. So this is just an additional cross term that shows up in the metric. Hopefully they'll actually explain where this metric comes from. I don't think that they will. So let's try to reason it out. So, if f is 0, which it is if you're just in the standard rotating... Okay, no, this checks out. If f is 0, which it is if you're outside the warp bubble, then this is just the normal rotating cylindrical coordinate system. If, on the other hand, f is not 0, then your angle is going to essentially increase faster. It's going to increase faster because you're rotating. And it's going to increase faster by an amount that's related to the speed that your warp bubble is moving at, and the speed of the rotating coordinate system. Then there's this extra term here, which actually doesn't show up in either term, which is interesting. That I'm confused by. However, if omega is 0, then it does reduce to the original one. So why is this term here? Well, maybe we'll just buy it and see what they have to say. So this is the d phi squared. Let's just believe them. I mean, it does reduce to the normal rotating one. If you set f to 0, then you get the normal rotating cylindrical coordinate system, and if you set omega to 0, you get the Alcubierre system. So maybe this is actually like a good compromise. But we'll see. Okay, so this is the metric. This describes the space-time curvature for this rotating cylindrical spinning warp drive. Then they say the tangential light cones. So again, this is how fast light is traveling in front of you and behind you, with f equals 1, so if you're on the warp drive. This is the speed of these light cones. And you can roughly figure this out just by essentially setting the left-hand side of this equation to 0. And then you can just solve for d phi dt. That's roughly what we're doing here. That'll give you v sub c. And this gives you the speed here. That should be pretty easy to see. You just look at this term here. Sorry, not that term. Well, there's some algebra to do, but in principle, it's doable. Where were we? Right, okay. We'll presently show that the condition... okay, we should look at this. So if the light cone the light that's moving in front of you, that's moving with the that's moving like ahead of you, that has a speed of light that's faster than the speed of light, because it's moving with the rotating coordinate system. And you can tell that because there's a plus here. And if it's moving away from you, then there's a minus. Okay, fine. Fine, okay. So the point in question, I guess, is they're going to show that the condition v sub s plus 1 times omega r, which is down here, if that's less than minus 1, this leads to a transition of the plus solution of v sub c, this speed of light, from positive to negative, is a necessary condition to allow locally time-like trajectories to exist which propagate backward in time as they travel around the loop. So, what they're going to say is that if you're moving fast enough, if you take the plus solution as omega goes? So if v sub s is negative, or if omega is negative, and you get that this product gets to be less than 1, then eventually you actually start moving backward in time. So imagine the space-time is rotating backwards, you're moving forwards, and so you'll get you'll be able to kind of catch up to your past self in some sense, I guess. So, where were we? So, we now ask how the metric of equation 5 appears locally to an observer on the rotating platform at a radius close to r sub s. So, I think that what they're going to... okay, yeah, so... Oh, isn't this what they just did? Okay, so imagine that you put somebody on the platform that's moving around. We want to ask, what does the space-time look like to them? Well, first, we move from the rotating frame into the lab frame. Why are they moving? Oh, okay, yeah. They move from the rotating frame into the lab frame by making the transformation phi sub z equals phi plus omega t. So first, they're going to step off and look at how the space-time looks from somebody who's not on the rotating platform. That's a coordinate transformation, which just amounts to basically redefining variables. So notice that they're writing phi sub z is phi plus omega t. So you can just substitute in all the place where you see phi, substitute in with phi sub z and t, and you'll end up with, oopsie daisy. Yeah, okay. You'll end up with this. This is just a fairly straightforward, coordinate transformation. It looks really nasty, but I don't actually think that we need to worry about what each term means right now. I mean, like you can like this is the time direction, this is the angle time mixing direction, this is the angular direction, this is the radial direction, this is and this is the z direction. But the actual coefficients don't matter because this is not the final step. And then they're going to move back into the rotating frame locally at a radius close to r sub s. So they were in a coordinate frame that was around the origin. So they were rotating with the origin. So they stepped out of the rotating frame. So now it's non-rotating. Then they're going to move and then they're going to step back into the rotating frame. So they move back into the rotating frame locally at a radius close to r sub s by making a tangential Lorentz boost by velocity minus omega r sub s. So they're just going to start moving at the tangential rate on the rotating frame. And so, oh, this is really quite nice. So then the metric reduces to this. So now it just looks like the Alcubierre drive, but it has one extra term, which is kind of funny. Though it has one extra term, which is a mixing of space and time. So the normal Alcubierre drive wouldn't have this term. It would just have this. But here they have a little bit extra because, I guess because the space-time is moving. The space-time is rotating. Yeah, they even say it here, where the dashes indicate boosted coordinates. Notice the similarity between equation 8 and equation 3. Equation 3 being this one. This is the Alcubierre drive with a circular trajectory, I should say. Which justifies the claim in the previous section that the metric of equation 5 represents an Alcubierre drive on a rotating platform. However, note that the metric of equation 8 is only valid close to the constant radius of r sub s. Yeah, that's fine. So this is an approximation. Also, the range of valid angles phi we can integrate the metric over should be less than 2 pi. That's also fine. If we reach 2 pi, then we have to come back to where we began, and due to lack of simultaneity in the Lorentz boost, there will be discontinuous jump in the time coordinate. Okay, this is all details. The point is this is a good description of the space-time near the actual Alcubierre drive doing the rotating. This jump is a well-known feature of... Oh, okay, so actually, really what they're doing here, they kind of have now... Okay, this makes sense. They've kind of now justified where this formula came from. Basically, they showed that if you look into the space-time near the Alcubierre drive, it looks like an Alcubierre drive rotating at about a point should look, which justifies that this was the place that they started from. If this had been different, they would have ended up with a different result here, and then it wouldn't have looked how they wanted it to look. So that's the justification. Where were we? Okay, so they actually do mention... Actually, apparently this is important. They say, this jump is a well-known feature of local metrics in rotating frames, but will take on special significance here. So apparently the jump is actually important. So we'll see what they have to say about that. Now, in the last section, we noted that a particle moving along the bubble in the metric of equation 3 being the warp drive moving around in a circle, that the metric of equation 3, i.e. following a circular trajectory at radius r sub s with tangential velocity v sub s, will be following a locally time-like trajectory even if v sub s is greater than 1, meaning v sub s is greater than the speed of light. Here, in these units, the speed of light is 1. This will also be true for the metric of equation 8. So all they're saying is that a particle could exist in the warp bubble described by this formula because it's the same. It's the same formula. It is easily shown that the components of the forward velocity for such a particle in the local metric are this. So this is basically describing the motion of the particle. So they're saying that you move through time at a rate of 1 second per second, basically, and you move through space, angular space, at the speed divided by the radius, which is fine. Your radial position isn't changing, your vertical position and the z direction isn't changing. Notice from the time component, we have dt prime equals d tau, indicating that the clock of the time traveler in the bubble remains synchronized with that of an observer at radius r sub s, not in the bubble. So the point is that the bubble, if somebody is just on the platform rotating, the clock of the person on the platform rotating and the clock of the person in the warp bubble, they remain synced up. So like there's no time dilation or weird stuff happening. Now, this is where things are going to get weird, I imagine. Thank you for the rose, Rush. Making a coordinate transformation to the rotating cylindrical coordinates, we find that the components of the forward velocity, so now they're transforming back to the rotating cylindrical coordinates, to this coordinate system, we find that the components of the particle forward velocity with respect to the global metric are this. This is probably going to be weird. Because, yeah, so this is, yeah, it's exactly this. And they're about to point it out, so I'm not going to spoil it. The tangential velocity of the particle trajectory in the global metric is v sub s prime. That's just the tangential velocity. This is the radius times the angular velocity. And then they can do some chain rule. right, r d phi d tau dt. By the way, tau is proper time. It's the amount of time that you actually see on your wristwatch. And so you can express what d tau dt is using this metric here. And that's how they get this formula here. Because of the fact that we have these expressions for the velocity. So they know what d tau or dt d tau is, for example. So, and the relationship between the proper time of a clock carried on this trajectory and the coordinate time is this. So, d tau is the time measured on your clock, dt is the coordinate time. So, sorry, I had a bug. Importantly, if this becomes negative, this denominator becomes negative, then the proper time will run backwards relative to the coordinate time. That's the really strange thing, and they're going to mention that. So let's look. They actually gave us some diagrams here, which is super nice. In figure 2, we plot the particle trajectory in the light cones in terms of both the local metric coordinates and the global metric coordinates. Let's take a look at this. So we have space-time diagrams showing the tangential light cones and the bubble trajectory in terms of A, the local coordinates, and B, the global coordinates. In the local coordinates, the light cones tip over sufficiently to allow the particle trajectory to exceed the speed of light. In the global metric, the forward light cone becomes directed back in time, allowing the particle trajectory to also be directed back in time. The parameters are v sub s equals 2 and omega r is minus 0.75. So here are the rotating coordinates. The platform that's rotating is moving at 3/4 the speed of light one direction, and the warp bubble is rotating around twice the speed of light in the other direction. So here we have, where's the actual light cone? Is it, why didn't they tell us what's what? I imagine blue and yellow are the light cones. Yeah, blue and yellow are the light cones. Okay. So here we have in A, the local coordinate system. So in the local coordinate system, meaning that with respect to somebody who's moving on the cylinder, who's moving on the platform, you're moving forward in time, no problem. The dotted line is your trajectory if you're in the Alcubierre bubble, and the blue line is the light that's traveling behind you, and the yellow line is the light that's traveling in front of you. There's no problem. You're moving forward in time. However, with respect to the global coordinate system, the coordinate system of somebody who is stationary, now those light cones tip over. So look how the solid blue line is tilted a little bit, and the yellow line has just completely turned. So here, now, your trajectory actually moves backwards in time. So with respect to somebody on the ground, with respect to somebody on the ground, not on the moving platform, you can move backwards in time. And that's very, very strange. So they're going to give us some examples. Let's work these out. So we now discuss two examples of time travel in this spacetime and analyze them in terms of both the global and local metrics, and use the example parameters in figure 2 to obtain numerical values for the time taken according to the traveler and the time traveled into the past as observed locally and globally. Consider a particle moving along with the bubble, i.e. following a trajectory of constant r equals rs, z equals 0, and maintaining a tangential velocity given by v sub s with phi of t being phi sub s of t. This is just the rate at which the Alcubierre drive is moving in a circle, which is fine. The Four velocity of such a particle was discussed in the previous section, and it's given by equation 9 in the local metric. It's this guy. Or equation 10 in the global metric. This guy. First, let us assume that v sub s of t remains constant over a time interval t equals 0 to tf. So you're not speeding up, you're not slowing down, it's constant for some long duration time, which is long enough to allow the particle to make at least one entire circuit at constant velocity. So the point is you actually have to come back to where you started. We wish to calculate the proper time interval experienced by the particle and the time interval of an observer who is far enough away to not be affected by the bubble. So, this is going to be very weird. First, we calculate in the global metric. From equation 10, we have that d phi d tau. This is equation 10. We have that d phi d tau is given by this formula. It's roughly this term here. Just evaluated at r equals r sub s. And so that's d phi sub tau. It's exactly this term. And hence, the total time experienced, you can just invert this equation, solve for tau, and then integrate. Basically, you're multiplying both sides by d tau and then dividing by this on both sides. So you get d phi over that equals d tau. Integrate both sides and you get the total time experienced. This is what physicists do. You can integrate over one full loop. You're making one full loop. That's 2 pi radians in the angular trajectory, and you get this value. You get a total time which is related to the distance distance away from the center that you are, the speed that you're rotating at, and the speed that your Alcubierre drive is moving at. They then say from equation 12, which is over here, this relates the time, the proper time, to the coordinate time. Oops. From equation 12, they get that the coordinate time experienced is here. So, one important feature is that if this is negative, v sub s omega r sub s, then the coordinate time experienced will be negative, which is very weird. They're going to give us some examples, so we'll see. In obtaining these results, we're assuming that the initial times at the beginning of the journey are tau sub I equals t sub I equals 0, so they're just starting the stopwatches at the same time. Using the same parameters as in figure 2, which was the Alcubierre drive is moving twice the speed of light, the rotational rate of the platform is moving at 3/4 the speed of light in the opposite direction. They find that tau sub f is 4.75 r sub s. So the person's watch will move forward at a rate of 4.5 units, or 4.75 times the distance from the center, units. That would be in like seconds, I suppose. But the proper time is negative. Sorry, not the proper time. The coordinate time is negative. So after completing a single circuit, the particle has aged by 4.75 r divided by c seconds, but it arrives back at the origin 3.9 r sub s divided by c seconds in the past. So here, because the platform is rotating one way and the Alcubierre drive is going in a circle the other way, this person is wound up in the past by traveling forward in time, which is very bizarre, very, very weird. So that's in the global metrics, the global coordinates. Now let's perform the same calculation in the local metric. From equation 9, that's this guy here. This is the speed in the local coordinates. Where were we? We have r sub s d phi over d tau is r sub s d phi over dt prime equals v sub s. So okay, so they're just calculating the speed, the tangential speed in these coordinates, which is fine. This implies that that tau sub f is x prime sub s over v sub s. So how do we read this? Oh, okay, yeah. So they're just saying that, look, the tau should be the same and regardless of the coordinate system. Regardless of the coordinate system, the time should be the same. So you can just solve. Sorry, so and you can integrate out r sub s d phi. That's the locally measured distance around the circuit. That is just the distance that it takes to go around the circuit. That's x prime sub s, and then you just divide it by v sub s and you get tau. That's totally fine. There's no issues there. It's just roughly solving for tau from this equation equals v sub s. Given that the circumference of the circuit is x sub s equals 2 pi r sub s in the lab frame, and taking account of the lab frame, by the way, is like the reference frame of like the person who's stationary, not the person moving around in the circle. And taking into account the Lorentz contraction between the lab frame and the local frame, because the local frame is moving, x sub s is given here. So there's Lorentz contraction because the rotating platform is rotating. And so the distance traveled around the rotating frame is different. And so in particular, you have to modify x sub s prime. And so apparently, if you substitute in x sub s as 2 pi r sub s, and then you substitute in for tau sub s, you get the same answer that you got in equation 14, which is good. It means that everything's consistent, that regardless of the system that you do the calculations in, you get the same watch time, which is the proper time. As expected. Good. Now, in order to calculate the time t prime sub f, this is told locally by a clock at the origin, we need to account for the fact that due to the Lorentz boosts leading to the local metric, there's a lack of simultaneity between the clock at phi equals 0 and the same clock as described at phi equals 2 pi. This is getting kind of confusing. But roughly speaking, going around the clock all the way around once means that you're at a different position in space-time. And so you have to take into account that the system is spinning. And so there's a Lorentz boost, and you've traveled a distance, so that Lorentz boost kind of leads to a divergence in the local times. I don't know how else to explain that. But this is the whole relativity of simultaneity. It's a pretty common thing in relativity. Anyway, this lack of simultaneity, delta t prime, is described by the usual simultaneity relationship. Delta t prime is x sub s v sub b divided by the square root of 1 minus v sub b squared, where v sub b is the speed. It's omega times r sub s. This is the boost, and x sub s is 2 pi r sub s. Fine. This is the separation in the unboosted frame. Let's see where they're going with this. Given that dt prime over d tau is 1... Oh yeah, because that is the... So dt prime is just the... dt prime is just the rate of change. Sorry, let me rephrase. T prime is the coordinate time for the rotating system. So of course, the proper time with respect to the coordinate time in the reference frame where the system is stationary is going to be 1. We conclude that the local time will be the proper time plus the lack of simultaneity correction. Hence, this formula. And so actually what it turns out that they get exactly t prime f is exactly the same modulo a term that goes as 1 over the square root of omega squared 1 minus omega squared r sub s squared. So everything is the same. So if you look here, if you look at this equation and you look at this equation, they're identical except there's a square root here. And that's just because of the square root as a result of the relativity of simultaneity. That's all that's happening here. So what they're doing is they're doing a double check. They're basically verifying that the calculations work out regardless of what reference frame you're in. Now, accounting for the Lorentz contraction between the global and local frame, we see that this is exactly what I was just saying. That t prime f equals tf times this square root factor, which is exactly what we expected. Okay. Sorry. So in this example, they've already shown us that time travel does happen. That they arrive back at the origin in the past. But they're going to consider a more interesting situation now, in which a particle starts off and finishes in flat space on the rotating platform. So they start off in the rotating platform in flat space. They end on the rotating platform in flat space. But at some point along the way, they join the Alcubierre bubble. So, all right, let's look at this. Okay, yeah. Let's look at this example. An Alcubierre bubble forms at phi equals t equals 0 and carries the particle around the circuit. The bubble disappears after the circuit, leaving the particle in flat space at the origin again, but at an earlier time. Okay, now this is bizarre. So the particle starts off, and finishes in flat space. So before t equals 0, the particle is just sitting there happy. It's just sitting there happy on the rotating platform, but it's an otherwise flat spacetime. But then an Alcubierre bubble forms. It's formed because they arrange the matter in such a way that it does so. It forms at phi equals t equals 0, and then because it forms where the particle is, it carries the particle around the circuit. And then the bubble goes away after one full circuit, and it leaves the particle back where it started. So the particle pops up, or the Alcubierre drive appears, goes around the circuit once, and then disappears. And this leaves the particle in flat space at the origin again, but at an earlier time. We assume that the velocity of the bubble in the metric changes as a function of proper time. Okay, that's fine. Such that f of 0 equals 0 and f of tau sub a equals 1, where f of tau monotonically increases between t equals 0 and t equals a, t equals tau a. So they're just saying that the bubble is going to speed up. Yeah, the bubble is going to go from 0 speed relative to the rotating platform to some maximum speed relative to the platform. Further, we assume that f of tau equals 1 for in some range, so it's staying at maximum velocity for a good amount of time. And then presumably it decreases. Here, tau sub f is again the proper time to complete the entire circuit. Yeah. So then it just decreases. Fine. And then it goes back down to 0 after it reaches the end of the bubble, the end of the circuit. Here, tau sub f is again the proper time to complete the entire circuit. We again assume that the particle moves so as to remain at the center of the bubble for the whole trajectory. Hence, its 4 velocity components in the global coordinates remain those of equation 10, but with v sub s equals v sub s of tau. So they're just still using these coordinates, or these this velocity here. And they're going to work in global coordinates, which I respect because the global coordinates seem easier. So we'll work in the global coordinates. Given the symmetry of the trajectory, it is sufficient to calculate the time to reach phi equals pi and then double it. That makes sense because it speeds up, maintains constant speed, and then it slows, and then it stays that constant speed and then slows down to complete the trajectory. So you only have to do halfway, right? And then you can just double it to figure out the full trajectory. Using equation 13, we can write, so equation 13 is this one over here. This is the rate at which the angle changes with respect to proper time. And so you can write phi 1. So phi 1 is how long it takes to get halfway around, right? Oh no, I'm sorry. What are they? No, this is not how long it takes to get halfway around. This is, phi 1 is the distance that you've traveled around the circuit in the amount of time it takes for the warp bubble to accelerate to max speed. So this is max speed here, tau sub a. And so this is how far you're traveling around in that time. So this is the integral that you end up doing. You're basically just integrating the speed with respect to time, you get a distance. So after proper time tau equals tau sub a, the particle has reached phi equals phi sub 1. Exactly. Okay. Given that f of tau equals 1, for tau sub a is less than or equal to tau is less than or equal to pi, then the proper time for the particle to go between phi sub 1 and pi is then just this. So they're just subtracting off what the... So they're just subtracting off the amount of proper time it took to get up to max speed from the amount of time it would have taken to get there from max speed. So that's why that's just pi minus this angle here. The total proper time to go around the circuit is then, so now they're just doubling this. They're adding tau sub a plus tau sub 1 and then doubling it. Yeah, so tau sub f equals 2 times tau sub a plus tau sub 1. And so then it's just as a formula from basically combining equations 17 and 18. And then, using equation 12, it's straightforward to show that the coordinate time for the full circuit, so they're going to have to plug in f of tau. And they also need... Yeah, they need using equation 12. Which one's equation 12? Equation 12 is here. Oh, that's just relating d tau to dt, which is fine. So they have what tau is. They need t. So here's the coordinate time for the full circuit. One moment. This is the coordinate time for the full circuit. All they've done is they've just solved for t in terms of tau from this equation, and then integrated roughly. And you end up with this lovely equation, which seems fairly simple. It is straightforward. It is straightforward once you do this a lot, but the point is they're kind of just shuffling symbols around at this point. So this term comes from this term. This 2 tau a comes from this term. And then this 1 over square root 1 minus omega squared to r sub s squared, that's coming from this term here. Roughly, and then they're adding some bits because... Why are they adding bits? I might have to work this out. Oh, I'm sorry. There's a piece here that I had neglected. that I can't ignore. That's where that's coming from. Right, okay. It is also straightforward to confirm that a consistent solution emerges from a calculation of the local frame. So all they're going to do now is that they're going to just do the same calculation of the local frame and come up with the same answer. To see that time travel is still possible with this protocol, let's assume a simple linear ramp function. So they're just going to assume that the time, that the warp drive will speed up linearly until it reaches a max speed and then slow down. Using the parameters from figure 2 again, we find that t sub f is this. This will be negative, and hence time travel becomes possible when r sub s is greater than 0.42. So when your rotating platform is bigger than, say, 0.42 light seconds, which is how we're measuring distances here, and your platform is rotating backwards at 3/4 the speed of light, and the Alcubierre drive is moving forwards at twice the speed of light, then time travel becomes possible. If this condition is not met, the particle will arrive back at the origin superluminally, but after it left. If the condition r sub s is greater than square root 7 over 2 pi is met, the particle ends up in flat space at the origin of the rotating platform before it left. If it remains there, it can become the particle that enters the bubble in the future, thus forming a closed time-like curve. More interestingly, if the particle moves away from the origin, it is traveling through its own past, and may interact with its past self before following a chronology-respecting path away from the bubble and into the future. So, all right, let's read the discussion and then we can talk about it. We can speculate on what a machine able to create the metric of equation 5 might look like. Suppose some future technology is able to create a device that via some means can produce the bubble curvature momentarily and on command. A large number of such devices can be arranged around the ring and pre-synchronized to fire in sequence in such a way as to create a bubble traveling at varying velocities, including superluminal around the ring. So they're imagining they create a bubble of curvature and then they just flash them up, a little bit of curvature all around the ring, creating in effect kind of an effective Alcubierre drive. Imagining this is all constructed on a cylindrical platform, then spinning the entire platform at high speeds would result in the desired metric. Yeah, no, this sounds like a not fun ride. Obviously, this is a Gedonken experiment. However, it does provide a clear physical picture for attaching to the metric and hence a solid basis upon which to discuss the apparent paradoxes that arise from considering time travel in general relativity. Very weird. In conclusion, we have described a global time machine metric which allows one to model particles which enter from a chronology-respecting past, interact with a non-chronology-respecting interval before exiting into a chronology-respecting future. Such situations have been discussed in the literature, especially for quantum particles, but always with the general relativity abstracted away. The simple form and clear physical interpretation of our metric suggests that it can be a key tool for rigorously modeling the dynamics of particles in such situations. Such abstracted versions also arise in research into indefinite causal structures and could also benefit from the metric discussed here. Ultimately, we hope that this will lead to a better understanding of the consequences for the union of quantum mechanics and general relativity and the potential existence of such spacetimes. And then there's some acknowledgements, some references. Let's scroll back up to the top. So the paper was called Spinning Up a Time Machine by T.C. Ralph and Chris Chang. I guess they're based in Brisbane. So this is a weird paper. So all of their calculations are fairly straightforward, and they do some double checks in several reference frames, and they agree. And so what that means, at least to me, is that unless they made the same mistake twice, then it seems like that their math is probably fine. Which means that if you could generate this rotating Alcubierre drive, then you really could do time travel. Now, I suspect that you can't generate a rotating Alcubierre drive for primarily the reason that the Alcubierre drive requires negative mass matter, but the idea is interesting nonetheless because it's like an explicit example of like actually traveling backwards in space-time or backwards in time. And you don't actually have to be in a closed time-like curve. You can just kind of like enter your path and then fuck off. Doesn't require any of these weird things where you kind of loop back to yourself and you're caught in like a time loop and you can never escape. So very, very bizarre, but very, very neat. Now, actually, I don't know, and then what? Then you can do whatever you want. I don't actually know if this has been published. It looks like it already was published in Physical Review D, which is a quite good journal. So, this checks out. So this has been published in a paper already. It's not quite peer review since it's already published, but the point is that I don't know. I really like this paper. I might even make a video about this paper because it's like a separate video because it's really neat. The picture that it paints is really, really cool. So that's it for today as far as peer review goes. Peer review. To everybody watching on YouTube, I hope you enjoyed. I'll see you next time.